Welcome to Radar in Action from the Fraunhofer Institute for High Frequency Physics and Radar Techniques, FHR. Today we talk about our radar target simulator Atrium, which will enable radar sensors to be a big support for autonomous driving. But before we start, we have a special guest today. Our director, Professor Dirk Heberling, will also welcome you.
Okay, good afternoon everybody who is following here. Good afternoon in German times. My name is Dirk Heberling, and together with my colleague Peter Knott, I'm head of this Institute Fraunhofer FHR. And we are very happy to welcome you to this edition of Fraunhofer Radar in Action, looking on automotive, which is really a topic that I personally very much support and follow, because this is a wonderful example of bring together a lot of know-how that we have in our institute to focus on a very interesting market and bring up advantages that we haven't seen up to now in the community. So please be open and welcome Thomas Dallmann for his presentation on this. Thomas Dallmann is head of our research group in Aachen, close to Aachen University, where I have my chair as well, and I'm very happy that we have this strong link to the Fraunhofer Institute. So, thank you very much, and I wish you a good presentation here, and hope that you find very interesting topics for yourself.
Okay, thank you very much for the introduction. So as was already mentioned, I will talk today about our system Atrium we are currently developing, but also I want to give you an overview about automotive testing in general, how it's nowadays done and what will expect us in the future. But first of all, before we really start, I want to address my thanks to the whole project team, which is actually responsible for setting all this stuff here up, because without them, I wouldn't be able to present you all these great results we can show you today. So a big thank you to the whole team. So let's really start at the beginning. What can really be perceived by a radar which is installed in a vehicle? So let's just imagine that on the right side, the car you see on the right side here, you have a radar equipped, and the radar is looking in the forward direction. And you are also seeing here on the left side another car, and this car can now be detected. So we can determine the distance to this car. We can determine the velocity of this car, which means that we can actually determine how fast it is going. And we can actually determine the angle or the direction of the car. So we can also determine under which angle it is oriented. What is, however, generated by the radar as a signal is what we call the raw data. So this is directly measured by the radar. And first of all, it really looks not that understandable. So if you would look at this data, you would have no clue what is going on there. So you need to do a lot of signal processing, which is following afterwards. So by signal processing, you can then generate the so-called data cube. And this data cube actually is like a heat map. So it contains different values along different dimensions. The dimensions are distance, angle, and velocity. And if you have a very high value in one of these cells, then this means that there is a target. So in this image here, you can see that there is a bright yellow spot, and this spot is actually the presence of a target. However, these data cubes are quite large, so you have a lot of data, and you are trying to detect the targets within this kind of data cube. And what you get out is a so-called object list, and the object list contains for each row you get actually an entry for a target or several echoes occurring at the target. So you see here, for example, a target at 52 meters distance at 15 meters per second under an angle of 10-degree azimuth and 0-degree elevation, and with an amplitude or with a brightness of 13 dB. This object list, however, is not where the radar normally finishes. Afterwards, there follow higher level functions, which are then, for example, tracking the target, so they're observing their movement, or they are classifying the target, so they are determining if this is a car or a passenger, for example, or a bicycle. And finally, more information will be given to the controller of the car, which will then interpret this information. If you want to test such a radar, then you have several test methods you can actually use. So you start normally with a road test, or that's actually the easiest what you can use in terms of how it actually works out. You just install the radar in the car and drive around with it. Then there is testing on hardware level. There you really take the whole radar system and you use certain measurement systems which allow to test how the radar behaves. And finally, you have the testing on software level, where you generate artificial data and feed it into the signal processing chain, and then check if the signal processing is working out properly. Let's have a look at all these categories here, and let's see what their specifics are. So road tests, we will start with the statistical tests. This is just having the car equipped with a radar and driving around within regular traffic. And normally this is done to determine the statistical error rate of the radar sensor. A good example is actually shown here. Here you see a cow standing in the middle of the street. This is quite an unexpected event, but this is something the radar sensor still has to handle, and what you still want to test and verify so that you can be sure that your radar is not behaving faulty even in unexpected situations. So you are trying to cover this aspect of the radar functionality. On the right side, you see that we can also build up scenario catalogs and test them on test tracks. This allows us to actually test for expected situations, like, for example, as you see here, an intersection. So you can drive with a car with the radar onto an intersection and test if the radar actually determines the environment in the way you intend to get it determined. Then you can test on hardware level. Let's start on the right side this time. There we have the analog signal injection, which means that we are using signal generators, for example, and signal analyzers to inject signals into the radar hardware and to read out how the hardware behaves onto this. So this is one way to test if the hardware actually works well. And the other functionality or the other measurement system you can use is an OTA testing system, which means over the air. These are normally radar target simulators, and these are the devices which we will talk mostly about today. These devices receive the signal which is transmitted by the radar, then they modify it in some way, and then they transmit it again. And by this, the radar, upon reception of the signal, thinks that there is a target at a certain distance. And it's shown here how this actually works. So you see now here in the lower part of this slide that there is an automotive radar within a vehicle, and the automotive radar transmits a wave onto an antenna array. Then we go into the radar target simulator, and this radar target simulator, first of all, does a lot of operations onto the signal, like, for example, delaying it, which will give you a certain distance. And by modulating a Doppler onto it, which will simulate a certain velocity, by changing the magnitude to make the target brighter or less bright, and by changing the phase. And you do not only do this a single time, but several times. So you will finally have n different copies of the signal, and these are all perceived by the radar as certain echoes, so certain radar targets or certain objects which are around the radar. By this, you can actually test the radar system and with it the whole hardware and signal processing chain. And finally, we come to the testing on software level. There we can actually generate raw data by, for example, simulation, and inject this raw data into the signal processing chain of the radar sensor, and by this test the whole signal processing chain. But of course, you can also generate higher level data, like, for example, object lists or the data cubes. It depends really on what you want to test about your sensor and where you want to really start. So what I want to show you now is what I call the magic triangle. So this shows you actually how complex and difficult and which challenges all these approaches have. Let's start with the road tests. Road tests are done in a real environment, so the complexity of the scenario itself couldn't be higher. It's just the most complex environment you can actually model and imagine. The number of considered system components is very high because you are actually testing software and hardware of the radar sensor and even parts of the car, like the bumper, for example, in front of the radar. However, it's really time consuming. So the problem here is that you need personnel, which is actually doing the testing. You cannot test 24/7 because you have to do breaks. Sometimes the weather is not appropriate. So the road tests really suffer from a lot of time and therefore also high costs. You can, of course, do testing on software level, which means that you inject either raw data or data cubes or object lists. This is very time saving because you can test 24/7 without a driver getting tired, for example. And also nowadays, these simulations are quite good, so the complexity of the scenario can be very high. So this is really an advantage here. However, you're just considering the signal processing chain and you're not testing the hardware. And this is a disadvantage of this approach. And finally, we have the testing on hardware level, especially the radar target simulators. They are also very time saving because you can test 24/7 and you can consider also the radar hardware. You can even place some parts of the bumper, for example, in front of the radar. However, the complexity of the scenario is not very high. And the reasons for that I will show you now on the next slide. So I will want to just give you now some idea why the complexity in radar target simulation is not sufficient. So imagine you are a radar sensor and you're looking at this scenario here. So it's a really rich scenario with a lot of cars, with a lot of infrastructure. Many reflections can occur there. However, what a radar target simulator can normally give you is just something which looks like this here. So just a very few echoes, actually, just a very few points you can see here. Perhaps they are on prominent spots like the cars, but still the complexity of this environment is not represented accurately here. And this is really the challenge of radar target simulators. So to just give you some numbers, state-of-the-art radar target simulators can generate just a single-digit number of echoes. Nowadays, they can generate them along the range and the Doppler, so distance and Doppler, and they can also position them along angle. However, the number of echoes is only in the single digit. On the other hand, we have radars which, for example, look like this. State-of-the-art radars, for example, have a range resolution which can be around 4 centimeters, an azimuth resolution which can be better than 5 degrees, so smaller than 5 degrees, and a velocity resolution which can be around 0.1 meters per second. This actually means that the radar can perceive targets at each 4 centimeters in distance, at each 5 degrees along angle, and even along velocity, it's even very high, 0.1 meters per second for each velocity. So you see that the radar itself can perceive a lot about the environment. It can really see a lot compared to what the radar target simulator can give you, which is just a single-digit number of echoes. This is actually what we try to address within our project Atrium. This is a test environment for automotive radars, which mostly aims at the simulation of complex traffic scenarios. So we are specifically addressing this complexity issue. And I want to show you how we are currently approaching it, which development steps we already have taken. So we have a single channel system which will be presented to you today. This is consisting out of a commercial off-the-shelf RF front end and can generate already up to 16 echoes, so more than a single-digit number. Then we have the extended single channel system, which is currently still under development, but almost finished, where we use a custom RF front end, which can generate more than 100 echoes. And finally, we are developing the multi-channel system, which then has a custom RF and a custom antenna front end, which can generate up to 300 echoes. And you actually see that we are a bit behind because of Corona. We are unfortunately in this situation, but still I am quite happy that I can show you some results of the extended single channel system already, because we have some very interesting news there. But let's first of all talk about the single channel radar target simulator. So you see here that we have mostly the same setup as you have seen before. We have the automotive radar in the lower half, and then you see that the wave is received by a single antenna. We have a single receiver here with quite a large bandwidth. Then we go into the digital domain using an FPGA. There we generate then up to 16 scattering centers or echoes. And finally, we have a transmitter which has just a bandwidth of 1 gigahertz. And this transmits then the echo or the waveform of the modified waveform of the radar sensor back to the radar sensor. And this means that with this system, within the frequency range of 76 to 81 gigahertz, we can generate targets. However, just for a bandwidth of 1 gigahertz, which is, however, for current radar generations mostly sufficient. We have only one channel so that we cannot cover an angular range. However, we can generate up to 16 scattering centers. And this will be presented by Torsten Mathy after this presentation. Then we are currently working on the extended single channel radar target simulator. As you see here, this system is a little bit different, especially if you look at the transmitter. The transmitter is designed in a way that it stretches a bandwidth of 100 megahertz up to 4 gigahertz. On the FPGA side, we therefore have a lot of channels available with lower bandwidths of just 100 megahertz. And on each of these channels, we can distribute a certain number of echoes, which is in this case much higher than these 16 echoes you have seen before. We are using a hardware component called a combiner here to direct all these echoes onto the single transmitter. And by this, we can still do just a simulation for one angle, but with much more echoes and also with a larger bandwidth, which has now 4 gigahertz. You also see that we patented the signal workflow of our FPGA here because we developed their signal processing approach, which actually allows us to generate so many targets in this efficient way. See here our current results. So we are still covering a frequency range from 76 to 81 gigahertz. For bandwidth of 4 gigahertz, we still have one TX and one RX channel, but we can generate up to 128 scattering centers. The RF frontend is currently quite a modular setup, so we are still improving it, but it already works. And on the right side, you already see our finished digital backend, which has 96 channels available, which will also be used, of course, for the multi-channel system, where we combine 31 channels, as you see, was a very early setup. During the live demo, you will also see the digital backend with the new combiner, which looks a little bit more interesting. Here you see some of these results we already were able to generate. We generated these just with the backend, so just with without the transmitter up to now. And you see here that along range and Doppler, which means along distance and along velocity, we can actually generate all these bright spots, and each bright spot is a single radar echo. And on the left map, you can see that we were able to generate 80 targets. And on the right map, you can see that we were able to generate 122 targets. They are just distributed arbitrarily. There is no meaning behind this. And we could configure the look and the orientation, the position of these targets in any arbitrary way along range and Doppler. So we have complete freedom over this. Finally, we are developing on the multi-channel radar target simulator, and I think you see in which direction this is heading. So now we are connecting several transmitters to all these connectors there, to all these 96 channels. And by this, we can then cover also the angular dimension. So we can cover several angles. We do this, however, by a setup, which you see on the right side as a proof of concept. We are using a very specific antenna front end here. We are still covering the same frequency range. We still have an IFBW of 4 gigahertz. We now have 96 TX channels, and we can generate up to 384 scattering centers with it, which is really huge. Just have a short look at the antenna system, which we also patented. We are using a double reflector structure here. You see this RUT, which is a radar under test. So there the radar is placed. You see in the lower half all these antennas here, which are actually used to distribute the transmit power onto the reflector. And we do this because by this we can actually shorten the cable lengths we have to use, and we can generate so-called quasi-planar wavefronts, which is what you actually want to receive by your radar system. It's just more realistic. So in summary, I can say that current test methods, as I have presented for radars, are either quite time demanding, or they are non-holistic, which means that they do not cover the whole radar system, or they do not permit sufficient complexity. And we are trying to address with Atrium all these three aspects here. We are trying to make over-the-air testing more versatile by this, as you have seen in the way we are currently doing it, we are setting up the Atrium system, which is both scalable and flexible and should be able to generate this huge amount of scattering centers. And by this, we really hope that we can address with it the future demands of the automotive industry and can allow to test radars as good as possible and make by this the road safer. The following, you will see the live demo of my colleague, Torsten Mathy, and therefore we will switch the cameras now. Up to now, I want to thank you for the attention, and if you have later on questions, we can answer them after the live presentation. Thank you very much.
Yeah, thank you, Thomas. Hi, everyone, and welcome. My name is Torsten Mathy, and I would like to give you a short live demonstration of our Atrium system. You can see here 4 devices. The upper 2 devices form the so-called single-channel radar target simulator, single-channel RTS. It consists of a digital unit with an FPGA, digital to analog converters, analog to digital converters, and an RF unit with a single receive antenna and a single transmit antenna. With this Atrium single-channel RTS, we are able to generate up to 16 point targets from one direction. In our live demo today, we will focus on that device. But before we take a closer look at the single-channel RTS, I want to show you the 2 further developments here below. You can see our multi-channel RTS. In contrast to the single-channel system, it has 96 digital outputs and is therefore able to feed more RF paths and transmitting antennas to synthesize targets from different angles. In total, the system is capable of generating up to 300 point targets. Another application is obtained by connecting 32 of these output channels to the lower system, to the lower device. These channels are combined to a single output channel. And in this way, we also get a single channel system, but this is now capable of generating up to 128 point targets. We call this combination the extended single-channel RTS. But now back to our first mentioned single-channel RTS, capable of generating up to 16 point targets. How does it work? We heard it already. The RTS receives signals from a radar under test and retransmits modified signals, which represents target detections in the radar. We have placed such a radar under test in front of our RTS. The radar operates at a frequency of about 76 gigahertz with a bandwidth of about 1 gigahertz. The online processing is done on chip in the radar, and detection results are displayed in the graphical user interface. Here we can see on the screen on the right side, the Atrium single channel RTS generates up to 16 point targets, and we see on the right side the graphical user interface of the radar under test. Detections are shown in the so-called range Doppler map, where the x-axis represents the range in meters and the y-axis represents Doppler or velocity, the Doppler frequency. As you can see, the RTS generates a specific scenario for demonstration purposes. It indicates our Atrium logo, as you also can see it here on the left. Yeah, let's now have a more detailed look on the Atrium graphical user interface, which is on the right. The whole system can be controlled with this software. For example, I have control for every single point target. I can select each of them. For example, delay, which means distance, or Doppler frequency, or the attenuation, the amplitude of each individual point target can be modified. But in addition, traffic scenarios measured and recorded by another radar, for example, or even simulated traffic scenarios can be transferred to the hardware memory of the RTS to transmit them back to the radar under test. And on this section here of the ATRIUM software, you find some predefined simulated or measured traffic scenarios which can be selected and transferred to the memory of the RTS. As an example, we prepared a junction traffic scenario with 4-point targets, and please observe the range Doppler map on the top here on the right when I press the start button. So the scene starts, and you can see some moving points, some cars that arrive the junction or leave the junction. Yeah, and you can see a playback of this predefined traffic scenario. Yeah, this brings me to the end of this live demo. Thank you very much.
Thank you very much, Torsten. Thank you very much, Thomas, for your presentation and the live demo. And there are many questions, so I go ahead. The first question, generally, advantages and disadvantages when comparing radar and LiDAR used by driverless cars, competing or complementing technologies. What are the typical radar use cases?
Yeah, I can state something about this. Of course, I'm not a LiDAR expert, I have to say. However, as I see it, I would say that radar and LiDAR are still complementing technologies, because they can actually be used in a way that they allow the fusion of the data, which is actually something most OEMs are seeking for to make the driving safer. So first of all, I think mostly nobody is really seeing radar as a technology which will be the only sensor technology within an autonomous car. So that's for sure. Of course, there are some advantages of radars which are not given by LiDARs. So even during severe weather conditions, we can use the radar in a quite a nice way. So the radar will still be working during these weather conditions, like, for example, snow, fog, hail. These would be cases where these systems would still work quite well. We can give a very precise estimation of the velocity of objects. This is not that easy using LiDAR sensors. But of course, there are also advantages of LiDAR sensors. For example, they have a very high resolution, which is something radars cannot compete with. But in total, I would still agree that they are complementing technologies. And if we want to achieve level 5, which is a complete autonomy of the car, we perhaps even need both technologies to really make sure that these cars are safe.
Okay, yeah, thank you very much. We have many questions, so it's now a special question. Can you spread a signal across the boundary of 100 megahertz bandwidth? Means create a 250 bandwidth signal that is broken across 2.5 channels?
I'm not completely sure how this is meant. We are not planning to go across these 100 megahertz bandwidths, since we can finally cover with our system bandwidth of 4 gigahertz using our specific transmitter setup. And then within these 100 megahertz, we, however, as long as we have a monofrequency signal, we can mostly do anything we want. And so this actually allows us to cover any FMCW approach you can imagine, and therefore we think that the system is quite able to cope with most of the FMCW signal forms. So we do not intend to get across this 100 megahertz boundary since we do not see that it is really required for this specific setup here.
Okay, thank you. Next question. 128 scattering center means you can generate 228 different targets with different velocity and distance?
Yeah, so this is absolutely true. We can generate 128 scattering centers with different velocity and distance. That is actually possible, and this is what we are actually intending with this setup. Yeah.
Okay, great. Is multiple reflection represented in this simulated scenarios?
This is actually the case. What I did not address during my presentation was the workflow we actually have behind this. We are using actually a whole electromagnetic simulation workflow, which allows us to generate these scenarios. So we are using a software we developed in-house, which we developed also within this project, which allows us to identify the scattering centers at the right spots at a vehicle. So we can put together scenarios based on CAD models. We can put into these scenarios, for example, cars and bicycles, and then we can simulate this using an EM simulation. And this EM simulation will also give us multiple reflections, just up to a certain degree, because we restricted this to keep the simulation performant, but we can consider this. And these reflections are then given to the radar target simulator and then replayed by the system. So yeah, we can consider multiple reflections.
Oh, great explanation. Too high for me. So we go, and there's another specific question. Do you also perform research into which scenarios to load into the hill simulator? If so, how do you verify them against real world scenarios?
Yeah, of course, identifying the right scenarios would be a project on its own, and it actually is yeah, a lot of research is going on onto this topic, which is the right scenario here. But at least we try to address this. We identified a set of scenarios, which is at least at the moment a set of scenarios which causes the most fatalities and incidents in traffic. So this was a basis upon we relied there. And these scenarios we did model, and these scenarios can be replayed by the radar target simulator. So this means we mostly have a scenario catalog which is usable for the radar target simulator. And in addition, we also support with the workflow to test against measurement data we acquired with radar sensors. So we can even validate these these simulation scenarios if we want to. Of course, this is just a start. Of course, we have the full flexibility to model any scenario we want here. So we are not restricted to the scenario catalog, but we have at least certain scenarios at hand which we can directly use. For example, intersections or highway traffic, and of course also urban scenarios.
Okay, we have many questions about the point. You mentioned that the target is a point target. What if the target has more than one scattering center? And additionally, do you have different signal models for different targets, people, cars, bikes?
No, we do not have different signal models for different targets, but there is a very good reason behind it, and that's what I actually already mentioned. Our electromagnetic simulation, our tool which we call GoProSim. This is a tool which will identify the echoes which can occur at a target. And there can be not only one echo, but several echoes. And these echoes can be spread across a target, and we will be able, due to the high number of scattering centers we can actually simulate, to represent all of them, even if they just belong to one target. So because we have so many scattering centers available which we can generate, we can actually distribute them just for one target. And this gives us actually the freedom to model a radar target with a certain target signature by representing each echo just by a single by one of these echoes we have available. So we can address this. We do not have specific models for the cars because these models are actually induced by the simulation we are undertaking. And since it's an electromagnetic simulation, it's very close to the physical reality.
In the current automotive radar market, which supplier seems to have an edge in radar technology? Can we say something about this?
I would be very careful about stating something like this. What I can state, however, is that you should not underestimate how far and how advanced these systems nowadays are. These are really complex machines which can measure a lot and which are really able to perceive the environment in its very complex ways. So this is, however, true for many manufacturers and for many sensors on the market.
Okay, so I think now we come to the last question, and you can point out what is the advantage of the system in comparison to simulation only?
Yeah, so the advantage is something I tried to mention also during the presentation. The advantage is that we can consider the influence of the hardware. We can consider the influence of the vehicle to a certain degree, like, for example, adding an emblem in front of the radar or adding a part of the bumper in front of the radar. And we really have free space propagation here. So we have mostly the environment the radar will live in, and this makes it, of course, much more realistic than just addressing the signal processing. Although the signal processing nowadays is a very important and the most complex part of a radar sensor, you still want to cover the influences of the hardware itself, and this can be achieved by our system. And actually, it makes it even very easy because you can just install the radar in front of the radar target simulator, and besides this, just use your radar sensor as you just would use it in the real environment. So you do not even need to make a lot of changes there. So that is, in my opinion, the advantage here.
Great. Thank you all. We have 8 minutes over time because of the many questions. We have over 20 questions. Very sorry. I'm very sorry that we cannot answer everything. If you have if you want your question answered, please send us the emails. Send the emails to Thomas Dallmann or me, and then we will answer it after the session. So, okay, I will make a view in the next week. And the next week we have the next English presentation, medical technology, new impulses in magnetic resonance imaging with metamaterials. We will show how metamaterials will improve the image quality of MRTs, and we will make a live view in the Fraunhofer Mewis in Bremen. Then we show in the research lab how it works in reality. So if you are not registered yet, you can register now, and the other dates you see on this page or visit our homepage, Radar in Action of Fraunhofer FHR. Yeah, so and at the end I would say thank you very much. Tomorrow you get a feedback form, very short, only 3 questions. It would be very glad of you if you answered it, and at the end of the week you get the slides of our presentation today. Then see you. Bye-bye. Until next week, I hope.